Hey everybody, this is Mr. Parliament, and this is a video tutorial for solving that lab challenge practice question on worksheet 6.4. Now this is a lab challenge I'd like to do in class. That's going to depend on when the next time I see you guys in class is, so we'll kind of see about that. But either way, I think this is a good practice problem because it is similar to some FRQ questions I've seen on past years' AP practice test. So the lab challenge itself would be different from this problem, mainly in that it's just simply a different shaped object. So anyway, the lab challenge practice question asks about a yo-yo being dropped while you hold the string versus a yo-yo being dropped while you don't hold the string. And part B asks you to kind of compare the fall times. So part A asks for an extended rigid body diagram for the yo-yo. So I've drawn that right here. We've got the yo-yo as a circular disc. We've got gravity acting downward at the center of the yo-yo. And we've got tension from the string pulling up at the edge of the yo-yo. Now probably for a real yo-yo, that tension would be somewhere more like here. And really, as the yo-yo falls more and more, that force of tension is going to move closer and closer to the center as the yo-yo unwinds. But we're going to make a simplifying assumption here, which is that we're assuming the yo-yo is wound up all the way with so much string that string is coming off the edge of the yo-yo. And we're also assuming that that radius that the string is wound to doesn't dramatically change over the course of the problem. And for only a 0.5 meter fall distance, that should be a pretty reasonable assumption. All right, so it tells you the yo-yo has a diameter of 7 centimeters across. So that would be a radius of 3.5 centimeters. And I went ahead and converted that to meters because we're going to use SI units so that the numbers work out in our equation. It doesn't ask for it for part A, but I also drew a force diagram because that's going to help my justification for part B. So we've got gravity going downward and tension going upward. Notice that in both cases, I drew gravity as greater than tension because in order for the yo-yo to fall, the force of gravity has to be greater than tension so that it can accelerate downward. I didn't draw the pivot point for part A. You usually draw the pivot point with a triangle. I'm going to draw that on the next slides because we're actually going to do two different solving methods that treats the pivot point about two different points. All right, part B asks which yo-yo is going to take longer to fall, the one where you're holding the string or the one where you just let go of the string and drop it. So I'm saying that the yo-yo with the string being held will take longer to fall, and my reasoning kind of takes two different forms. So one is there's an upward force of tension in the string, so therefore the yo-yo has to accelerate less than 9.8 meters per second squared. You guys know that if gravity is the only force acting on an object, it accelerates at 9.8 meters per second squared downward. So therefore, any upward force is going to make the yo-yo with the string being held accelerate at less than 9.8 meters per second squared downward. The yo-yo that's just dropped, of course, is only really going to have gravity acting on it. We can ignore air resistance, and therefore it would accelerate at 9.8 meters per second squared downward. My other reasoning is that in either case, you have some amount of initial gravitational energy to start with. And that's going to be the same for either yo-yo. It's the same mass, it's the same height, and it's the same acceleration due to gravity. For the case where the yo-yo unwinds, that's going to split between translational kinetic energy and rotational kinetic energy. For the case where the yo-yo is just dropped and it's not unwinding, all of that initial gravitational energy is going to turn into translational kinetic energy at the bottom. So translational kinetic energy is the one that determines how fast you're moving in a straight line, 1/2 mv squared. So therefore, the yo-yo that's just being dropped without you holding the string is going to have more translational kinetic energy at any given point in time than the yo-yo that's unwinding. So therefore, the yo-yo that's just dropped without holding the string is moving faster at any point in time, and therefore it will have a lower time to fall. All right, so there's part B. So before we start talking about part C, I want to talk about my color coding. So this is a kind of dense slide, so I figured having a nice color scheme to it would help kind of guide you guys visually. On the first video I made for you, we did one triangle in one color and one in the other, and I thought that kind of helped differentiate the two triangles considering I drew them on top of each other. So the whole idea behind the color scheme for this problem is that I picked a color for each variable, and I wrote the numerical value for that variable in that color. So for instance, if you look at this equation right here, I wrote it out in terms of variables to start with, and then when I plugged in numbers for those variables, I used the appropriate color. So moment of inertia is kind of this peachy color. So if you look at this equation and you're wondering, oh, where did 0.0001837.5 come from? Well, that's the moment of inertia. This kind of dark purple is the radius, and so on and so forth. So hopefully that kind of helps guide you guys visually in terms of where these numbers are coming from. All right, so I redrew my extended rigid body diagram for part A. For this solving method, I'm going to treat the pivot point as right here. And that's the point where the string is pulling up on the yo-yo, so that's where it's unwinding. So I'm treating that as the pivot point. So I've drawn that purple triangle right there. And otherwise, this diagram is the same. I went ahead and calculated the force of gravity because we're going to need it. It is a 100-gram yo-yo, so that's 0.1 kilograms. 0.1 times 9.8 is 0.98 newtons. I also figured that since the yo-yo is unwinding, we're going to have to use the sum of the torques equals I alpha. So we're going to need the moment of inertia, I. So let's just go ahead and calculate that now. So I is in this peachy color, and I equals for a flat disk rotating about its central axis. Moment of inertia is 1/2 mass times radius squared. So 1/2 times a mass of 0.1 kilograms times a radius of 0.035 meters. And that whole quantity is squared. That right there would give us the moment of inertia about its central axis right here. But our pivot point is over here. So we need to use the parallel axis theorem. Parallel axis theorem is that the new moment of inertia equals the moment of inertia about the center of mass plus md squared, where d is how far you've moved the axis of rotation. So I'm going to add to that moment of inertia 0.1 kilograms, the mass of the yo-yo, times the radius of the yo-yo squared, because we're moving it one yo-yo radius to the left. So I wrote the parallel axis theorem out in this teal color right here and labeled it as parallel axis theorem because I've noticed that students often forget to use the parallel axis theorem, so I figured it'd be very clear that's where this comes from. All right, so plug that into your calculator. You should get a moment of inertia for the yo-yo of 0.0001837.5 kilogram meter squared. So obviously I saved more sig figs than I really have in this one. I'm just going to save all the rounding to the end because that's what I usually do on lab challenges to get as precise an answer as possible. I know some of these decimals are unnecessary. Also notice it's a really small number, just like our moment of inertia for our donuts was. Typically, any object you have that has a radius or length, depending on which moment of inertia equation you're using, less than a meter, will often have a very small moment of inertia because you're squaring that radius or length. And as you guys know, any decimal between 0 and 1 gets smaller when you square it. And then also it's less than a kilogram, so that's gonna, well, in fact, it's 1/10 of a kilogram, so that's where at least one of these zeros comes from. All right, so as mentioned earlier, we're going to use torque equals I alpha. and, the sum of the torques equals I alpha. And the sum of the torques would be the torque caused by the force of tension, which the force of tension is at the pivot point, so a radius of 0, so Ft times 0. You'll notice that for these problems that any force at the pivot point won't provide any torque because r equals 0. And then minus the force of gravity times the radius, because the force of gravity is acting one radius away from the pivot point. That's a negative number, because that force of gravity would tend to unwind this yo-yo clockwise, and clockwise is negative on our unit circle. So we're going to go ahead and solve all this for alpha. So divide both sides by moment of inertia, and then I plug stuff in. So 0.98 newtons is the force of gravity, 0.035 meters is the radius, and then that number right there is the moment of inertia. And then plug that into your calculator, you should get 186.7 radians per second squared. Now, the units for this number are interesting. You guys know that a newton is a kilogram meter per second squared. So newton times meter would be kilogram meters squared per second squared. That kilograms times meters squared would be canceled out by the units of the moment of inertia. So kilograms cancel out and meters squared cancel out. That would leave us with 1 over second squared as our units. And you guys know that a radian is technically unitless. It's the ratio of arc length divided by radius. So meters per meter is a unitless number. So that's why this would technically give you 1 over second squared. That doesn't mean that it's like hertz squared or anything. That unitless number 1 represents radians. All right, so we've solved for alpha. Now, we're interested in how long this yo-yo takes to fall 0.5 meters. So we have an angular acceleration, but we have a linear distance. So we're going to have to do either convert our linear values to angular values or angular values to linear values. Either way would work. The method that I think makes the most conceptual sense to me is we're going to find out what angle the yo-yo has to unwind to so that it traces out 0.5 meters. Because every time the yo-yo makes one full rotation, the string length is going to increase by 1 circumference, and the yo-yo is going to fall by 1 circumference. So we want it to fall 0.5 meters. So arc length equals theta times radius. So 0.5 meters equals theta times 0.035 meters. Rearrange and solve for theta. You get 14.39 radians. So this yo-yo is unwinding a little bit more than 2 times in its fall, which I think is reasonable. It's a pretty short fall. So we then want to find, we're going to use the first kinematic equation for rotation. So our change in theta equals 1/2 our angular acceleration times time squared plus our angular velocity initial times time. We're starting from rest, so that initial angular velocity is 0. So delta theta is 14.29 radians, as we found earlier, equals 1/2. Angular acceleration is 186.7 radians per second squared times time squared. So rearrange and solve for time would give you square root of 2 times 14.29 divided by 186.7, which comes out to a time of 0.39 seconds. All right, so it's going to take the unwinding yo-yo 0.39 seconds to fall. Now, it's kind of quick about my work here, but we could also use the linear kinematic equation for the dropped yo-yo, accelerating at 9.8 meters per second squared, to find that it would reach the ground in 0.32 seconds. So we were right in part B, that the unwinding yo-yo does take a little bit longer. So this is the solving method that I learned when I was taught this lab challenge at an AP summer conference, and the instructor said, hey, it's a cool one because you have to use the parallel axis theorem, and that's a good axis theorem to practice. And I kind of convinced myself that this yo-yo is unwinding around that point because that's where the string is. But a few years back, Jack Holland solved this problem treating the pivot point at the center, and the more we talked about it, the more I realized that really the yo-yo is unwinding about its center. It's not unwinding about this point. If the yo-yo unwound about this point, then it would like kind of swing over this way. A good way to kind of find where your object is unwinding about, if it's moving linearly, is what point on the yo-yo moves in a straight line. And the only point on the yo-yo that's going to move in a straight line is the very center of it. This point right here is going to move down and clockwise. So really the yo-yo is unwinding about its center. So we're going to go ahead and solve this problem with the yo-yo unwinding about its center. So here is my extended rigid body diagram again. Only two differences are, one is that I've drawn my pivot point in the middle. The other is that we're actually going to solve this problem symbolically and then only plug in numbers at the end. And the reason I want to do that is some very interesting things cancel out in this problem, and I wanted to talk about those things as they cancel out. The same things cancel out in the other solving method, but I think it's a little bit more obvious why those things cancel out solving it this way. So instead of plugging in values, I'm just going to say that Fg equals m times g. And the moment of inertia in this case is 1/2 m r squared. We didn't have to use parallel axis theorem because it is unwinding about its center, so we can just use the equation off of our moment of inertia table sheet. All right, so the sum of our torques is going to equal the negative of the force of tension times the radius. We'd also have mg times 0, just like we had for tension last time, but I left that off because we know it's going to be 0. Again, it's a negative torque because this upward force of tension is going to tend to unwind the yo-yo clockwise, which is negative. So that one torque, from the force of tension equals I alpha. We also know that linear acceleration is equal to angular acceleration times radius. So we can rearrange that. Our angular acceleration equals our linear acceleration divided by radius. And here I have A in the dark blue because from here on out I'm going to be solving it in terms of linear acceleration, whereas the last one we used angular acceleration. All right, so I can plug all that in together. Basically just taking this and plugging it in here, and we get the force of tension times radius equals our moment of inertia times our linear acceleration divided by radius. So if I solve that for A, we get negative force of tension times the radius squared divided by the moment of inertia. Plug in our moment of inertia, and first we'll see right away that this radius squared canceled out. So this purple r squared is from, we got a radius here and a radius here, so that's just solving for A, we get r squared. And then this r squared is from the moment of inertia equation. So, assuming that force of tension does not depend on the radius, the acceleration of this yo-yo does not depend on the radius of the yo-yo. So if we doubled the radius of the yo-yo, it would fall at the same rate. And I think that's a little strange because you could look at it and be like, well, that would mean that this force of gravity is at a bigger radius and this force of tension is at a bigger radius. So that would provide more torque. Well, that's true, but it would also have a higher moment of inertia. So there'd be more torque, but there'd be more resistance to angular acceleration, and those two would cancel each other out, thus having the same angular acceleration. All right, so the r squareds cancel out. Flip this 1/2 in the denominator, and you get a linear acceleration of -2 times the force of tension divided by mass. Now, that would be the acceleration as a vector, where negative is downward, but I've decided to just look at the absolute value, the magnitude of acceleration. So we're going to treat acceleration as positive, and we're going to treat the force of tension as positive. And the reason I'm doing that is we have two different systems here of positive and negative. For all of the linear math we're going to do, we're treating it as one direction is the positive direction and one direction is the negative direction. So maybe downward is negative and upward is positive. For all our rotational stuff, we're treating it as clockwise is negative and counterclockwise is positive. So those two conventions don't really match up. The problem would be the same if the string was unwinding here, but all of our angular equations would tell us that we'd then have a positive alpha rather than a negative alpha. So I'm just going to drop the vector nature of both things and just look at the magnitudes. And we can do that as long as we're very careful about the operators we use. All right, so that's why I drew these arrows here saying that both of these are positive. I've also left this 2 over m in the peach color for our moment of inertia because I want to be clear as we move forward that this 2 over m came from this equation right here. So I'll kind of leave everything in its appropriate color so at the end, when we've seen everything that cancels out, we can see what remains, what factor actually changed our final value for our linear acceleration. All right, so we've kind of done everything we can with our sum of the torques equation at this point. And we have an equation with two unknowns, our linear acceleration and our force of tension. So we're going to use a sum of linear forces to solve for one of those unknowns. So the sum of the linear forces equals the force of gravity, which again, we're calling all of these values positive, getting rid of their vector notation. So force gravity, we're just going to say is a positive number, minus our force of tension, which is also a positive number. So if we were doing this with vectors, we would say Fg plus Ft, where one's positive and one's negative, but I'm basically taking into account the fact that gravity and tension are opposed to one another with this minus sign. So gravity minus tension is equal to mass times acceleration, and we're going to treat acceleration as a positive number. So since we know already that gravity is greater than tension, that's why I did gravity minus tension rather than tension minus gravity. All right, so rearrange and solve for the force of tension. We get m times g minus m times a. And then we can take this equation for force tension and plug it into this equation for acceleration. So that's what's happening right here. And that gives us our linear acceleration equals 2 over our mass times this equation right here in parentheses. So mass times 9.8 meters second squared downward minus mass times acceleration. You can cancel the masses out because if you factor out m, it would cancel with that m. And then distribute the 2, leaves us with our linear acceleration equals 2 times our acceleration due to gravity minus 2 times our acceleration. So rearrange, get a on the same side, so add 2a to either side. You get 3 times a equals 2 times g. So solve for a, you get our acceleration is 2/3 of our acceleration due to gravity. So notice that mass also canceled out here. So not only does the radius of the yo-yo not matter, the mass doesn't matter. And I think that one's more intuitive because usually when we have these problems of an object being dropped, the mass does cancel out because the acceleration due to gravity does not depend on mass. So really, the only thing that mattered for finding our linear acceleration was the shape of the yo-yo. The 2/3 number comes from our equation for the moment of inertia of the yo-yo. So this would work for a few other shapes as well, with the radius canceling out. It would work for a solid sphere, a hollow sphere, a hoop. We would get a different ratio here, but we would also have radius cancel out. It wouldn't, however, work for a thick-walled cylinder, because for the thick-walled cylinder we have that, um, you know, parentheses r1 squared plus r2 squared. So the r's wouldn't cancel out anymore. But for many of our shapes, the r's would cancel out, and we would just get some proportion of gravity as our acceleration. All right, so now we'll actually start plugging in numbers. So 2/3 times 9.8 is 6.53 meters per second squared. So then we can just use our kinematic equation, our change in height, times 1/2 acceleration times time squared plus v naught t, where our initial velocity is 0. Rearrange this and solve for t. You get the square root of 1 over a. So square root of 1 over 6.53 meters per second squared is 0.39 seconds. So this solving method really gives you the same answer as the other one, although this one is about the true pivot point of the object. So I'm not really sure why either pivot point works, but the year that that student, Jack Holland, showed me that this solving method worked, we tried this solving method with all symbolic values and showed that it also got us to an acceleration of 2/3 times the acceleration of the gravity. So in either case, we had the exact same value for the acceleration. So therefore, either solving method is exactly the same. It's not like we're just getting about 0.39 for both answers and they're within rounding difference from one another. They are mathematically the same answer. So anyway, either of those solving method works for this problem. I thought that this one is a little bit easier in, kind of mathematically because we know a value for the force of gravity. For this solving method, we have to leave the force of tension as a variable for quite a while until we can get a second equation because we have an equation with two unknowns here. So anyway, those are my two solving methods for the yo-yo being dropped while the string is held. You can see that in either case, whichever solving method we use, we have the yo-yo staying in the air for 0.07 seconds longer if you're holding the string. All right, so there is that lab challenge practice question on worksheet 4. Please feel free to email me if you have any further questions. Thanks, goodbye.